Assalamu alaikum. How are you doing, guys? Today I'm gonna discuss or explain the deflection of beam using the moment area method. Before we start, there are usually two methods of computing deflection. One is what we call geometric methods, and the other one is called work energy methods. As far as geometric method is concerned, this depends on the geometric shape of the deflected shape of structures, like what we did last time. And there are two methods or two techniques, if you will. One is the moment area method and the other is the conjugate beam method. Oh, to be more accurate, there are more than that, obviously, but these are the two that we are going to be discussing in this course. As far as the work energy based methods, there are also a couple of other methods, but we are only going to be interested in the virtual work method. All right, so we're going to be discussing the moment area method, conjugate beam method, and virtual work method for computing our deflections. And I'm going to first start with the moment area method. Now here I just want to show you, this is from mechanics of material, and this is basically showing you the relation between the change of angle or slope, which is equal to the moment over EI dx. Now EI usually is called the flexural rigidity of the structure. Rho is the radius of curvature here, and I'm not going to get into much detail because again this has been explained to you in the strength of material course, and I'm just putting that out for you because I'm going to use in the next slide d theta is equal m over ei dx. So if you have any questions regarding that, feel free to email me or see me in the office hopefully soon when we'll be done with this whole coronavirus crap. Excuse my French. Now, first of all, let's look at the beam that we have. So this is a beam which has some general loading on. You can see there's a concentrated force, P1, P2, there's some distributed loading, and then there is some concentrated moments. I'm going to draw the deflected shape or the elastic curve of that beam between 2 points, point A and point B. Okay, and then I'm going to be interested in some infinitesimal distance dx, which is at some distant x from B. Okay, so this is my dx now. I'm drawing a tangent at point A, which is this right here, and I'm drawing also a tangent at point B, which is right there. Okay, now the angle between the two tangents I'm going to call theta BA, which is telling me that this is the angle or the theta B measured from the tangent A. So I'm measuring it from this tangent, so that's why it's called theta BA. Okay, now with this dx and now this being d theta, so if I want the full angle, all I have to do is integrate from A to B, which is what I did over here. So again, d theta is equal to m over ei dx. Then theta BA is going to be the integration between A and B, m over ei dx. Okay, so what does this integration represent to me? So if I go back and look at this figure out here, you can see that this represents the area under the m over ei diagram. So this is, so what we usually do, we draw the bending moment diagram, divide that by ei. So this is what we are getting. So the first theorem of the moment area method is as follows. So the angle or change in slope between tangent of elastic curve at A and tangent at B equals the area under the m over ei diagram between A and B. So all we have to do is calculate this area right here, and it will give me that angle over here. Okay. As far as the sign convention goes, the angle is measured counterclockwise from tangent A to tangent B if the area of the M over EI diagram is positive. So here I have a positive bending moment diagram. And as you can see, going this way, I'm going counterclockwise. So this is my positive direction. So if I'm measuring from the tangent from the point at the left, okay, which is point A, so A is my left, going to a point to the right, which is here my B, okay, so then that rotation is going to be counterclockwise. All right, so this will take care of finding the change in slope between two points. Now, moving on to calculating this vertical distance between point B, which is on the elastic curve, and the tangent coming from A. So if I want this distance, which I'm calling TBA, so again, using that same change in angle that I did in the last slide, and now this being my delta T, okay, then this delta T, or the change in vertical distance, is equal to x times d theta. And think of it like this: if I have an arc, and then this is theta, if this is r, and then this is s, okay, then s is equal to r theta. Okay, and this is what I'm using over here, the same principle. So I'm saying that dt, this one here, is equal to x times d theta. Then dt would be x times m over ei dx. Then my doing the integration from point B to point A, and that will be equal to bax times m over ei dx. Now we know from statics that if I multiply x times area, I'm getting the centroid, or the first moment of area, where dA is equal m over eix. So that's why I'm taking x bar out. Then the distance, or the vertical deviation between point B and A. Again, this means the distance at B measured from the tangent at A is equal to the moment of the area about point B. Okay, so stating that, theorem 2 is the vertical deviation of the tangent at a point B on the elastic curve, so it has to be on the elastic curve, with respect to the tangent extended from another point, let's say A, equals the moment of the area under the M over EI diagram between the 2 points A and B. This moment is computed about point B, the point on the elastic curve where the deviation is to be determined. Okay, as far as the sign convention goes, so if my moment is positive from B to A, it indicates that the tangent at point B is above the tangent to the curve extended from point A. And since here we have a positive moment, then again this is telling me that point B is above point A. And that's going to help me in the future if I don't know how the elastic curve is going to look like. So if I just assume some elastic curve, and then for instance I got a negative area instead of a positive, then I know whether my curve is right and wrong, and I will talk about it more during the examples. So if, and you're going to see me using sometimes TBA or delta BA, it's the same thing. Again, it's the vertical deviation between point B on the elastic curve to the tangent coming from point A. So if this value is positive, then B is above the tangent. Okay, if it is negative, so let's say if I'm drawing this like that, and I'm extending a slope from point A, and then I'm saying that this is the drawing that I'm using. Let's say I got completely out of whack, and I said, no, this is how the elastic curve is going to look like. And then if I calculated dBA and found that to be positive, then I know my drawing is not correct, because now B is under A, and I know for it to be positive, B has to be on top of A, which means that my drawing here is actually not correct. So that's one of the way of knowing if my elastic curve is correct or not. Okay. Now, there are some standard areas that we are going to benefit from. So if I have a parabola, and we usually use that for when we compute the areas under distributed loads. So in this case, the area is going to be equal to 2/3 BH. This is B, and then this is H, and then the centroid, which is measured from the vertical right here, is 3/8 of B. If I measured it from here, then this is just going to be simply 5/8 B. If I have a parabolic spandrel, and this is usually when we have the overhangs or we have the cantilever, then this is going to take this shape instead of that shape. So in this case, then the area would be 1/3 BH, and then X bar would be 3/4 of B. If I'm measuring this way, it will be 1/4. Now, if I have a complete parabolic segment, okay, then there you're still 2/3. Now B is the whole thing, and H is that one, and then the centroid is smack down in the middle at B/2. And for our bending moment, then this usually is when H is equal to WB²/8, and I will show you some examples down the road on how to make use of this chart, right? So now I'm going to start off with an example. Okay, so here I have a beam loaded with a distributed load of W kilonewton per meter, and he wants me to find delta C and theta A. So now my elastic curve is going to be like that. So this is my assumed elastic curve. Then this is the tangent at point A. Then theta A that is required of me is this angle right here. Okay, again, which is the angle between the slope at point A and the undeflected curve or undeflected chord A, B, this one. And delta C is as indicated. So what it is required of me, it's required of me this distance and this angle, and we're going to show you how we are going to compute that using the moment area method. Now, here I'm drawing a tangent at point C, again, because I want the delta C. But what you will notice is that delta C is not equal to delta CA. Okay, these two are different. So these are not equal. Okay, and I can't find delta C using theorem 2. The only thing that I can find is actually delta CA. And this angle here is theta CA. Again, I am measuring. So this is the point to my right, and this is the point to my left, which is point A. So I'm going to go counterclockwise, and if it comes positive, then this is correct. So again, this is theta C measured from tangent A. This is delta C measured from tangent A. And remember that delta C, or for the moment area theorem, is always on the elastic curve. Okay? But one thing you're going to notice is that if I measure delta AC, okay, which again here A is on the elastic curve, which is a value of 0, and then this is the tangent coming from C. So this is delta A measured from C. Okay, so now having this in mind, we're going to first of all start calculating the angles. Okay, so now this is my M/EI diagram. This is my maximum moment WL²/8EI. Again, I want this, all right? And now this is my theta CA. Now, if you notice that the tangent at C has a slope of 0, again, because due to the symmetry. So this means that theta C measured from tangent at A will be equal to theta A. So by invoking the first theorem, then theta CA, again, it's the angle between two tangents A and C, and this is measured from A. It's going to be 2/3, which is the area of the first area that I shown you, times B, which is L over 2, okay, times the height WL square over 8EI. So this is my area, which was again 2/3 BVH, B being L over 2 and H being WL square over 8EI, and this being L over 2. So now theta CA is equal to WL cubed over 24 EI, which is the same as theta A. So now we got theta A covered. Now let's go to finding the deflection delta C. Again, just to re-emphasize, due to the symmetry, the maximum deflection is at the center of the beam, which is required. Slope at the maximum deflection is always equal to 0, right? Because at that point it's going to change curvature, or going to change slope. So I can assume, or I'm not going to assume, I'm going to make the distinction that delta CA, excuse me, this is actually not right. This is supposed to be delta AC, okay, which is delta A measured from tangent C, will be equal to delta C, but I'm going to take, which means I'm going to take the moment about point A. So now the area again is 2/3 times L over 2 times WL square over 8 times 5/8 times L over 2. Remember when we had that parabola like this, okay, then my 3/8 was from here, but since I'm taking the moment about this point A, then this is going to be my 5/8, okay? Hence 5/8 times, and this distance obviously is L over 2. So please make note in your notes to change that to delta AC and not delta CA, okay? So the maximum deflection is equal to 5WL to the 4th divided by 384 EI. So this is how we can use the moment area theorems to calculate the angle and deflection. Now there's another method or another approach I could use to calculate the deflection. I'm going to show that to you as well, because this is a little bit more involved. So again, I'm going to back now to maybe calculating delta CA, which is the deflection at C from tangent A, and this is my delta C. So now this right here, delta prime, which is this whole thing, okay, is equal to delta C, which I want, plus delta CA. Now this I can calculate because this is simply the moment about point C, or the moment under the area diagram between point A and C about point C. Delta C is required. Now delta prime, actually I can calculate it using the tangent. Here tangent theta A is simply delta prime divided by L over 2, right? So if this is my length, L over 2, and that whole thing is delta prime, this distance right here, then tan this angle is equal to delta divided by L over 2. And we know for small angles that tan theta A is equal to theta A. Then that means that theta A is equal to delta prime over L over 2, which means that delta prime now is going to be equal to theta A times L over 2, and that will be WL cubed over 48 EI. And just to remind you that theta A is, and we got that from the previous question, the previous slide, 2 slides actually, is WL cubed over 24 EI. Now going back to calculate delta CA, again that's the deviation from point C measured from the tangent at A. Always remember that the first point is always on the elastic curve and the second point is always the tangent. Okay, so delta CA, and this is the moment about point C. So now the area is still 2/3 L over 2 WL square over 8 EI. forgot the EI over here. Please add that. Times, again, now it's going to be 3/8 because I'm taking the moment about point C. So that's now the 3/8 times L over 2, and that's 3WL4 divided by 384 EI. Thus, delta C now is going to be delta C minus delta CA, which is WL cubed over 48 EI minus 3WL to the 4th 384 EI, and now that will be as previously found, which is the same answer. But this is a little bit longer, but here I just wanted you to show you how to use how can we use theta. Here the big thing was, since I'm talking about the maximum displacement, then I can assume that the slope is equal to 0. But I usually will use this technique if I need, let's say, maybe the deflection somewhere over here where the slope is not 0 anymore, and then I have to resort to this type of solutions. My next class or my next video is going to be probably more examples on this, about 3 to 4 examples, inshallah. And you guys have a nice